Welcome to the first episode of the Talkin' Science podcast, a podcast about the cutting-edge research and innovation in science, technology, artificial intelligence, philosophy, and more. We are your hosts,
Mark Yang
and Krish Gupta.
The following is a conversation with Fuentest Canek. Professor Canek is an associate professor at Northeastern University. His research includes multiple areas of physical optics, photonics, and organic electronics. I've known him personally as an undergraduate researcher at his Electrical Surfaces and Organic Interfaces lab. Professor Canek is a brilliant teacher and one of the most interesting human beings I've met at Northeastern. We had many conversations before today, which spurs the inspiration of today's episode. Without further ado, this is Fuentest Canek.
Good. Yeah. That's a heavy door.
It is.
Okay, so can you describe your research and basically what you do before our conversation or what you're working on right now?
Sure. So my research, the field of my research is organic electronics. And what that means is that we are trying to build electronic components out of organic molecules. The big difference that you get in with respect to inorganic semiconductors is that these organic molecules can be dissolved into solvents, so you can make inks out of those. And therefore, you can actually make electronics by printing techniques, right? From inkjet printing, slot die coating, roll-to-roll processes. So the big idea of organic electronics is that you can produce electronic components at a very big speed, but also to make electronics with form factors that you don't get with inorganic electronics, right? Such as flexible substrates, for instance, right? So that's actually what got me into this field, was kind of the allure of making flexible screens, flexible phones, right? Which now they're coming finally to the market, right? And so organic semiconductors, that's what it allows you to make, right? Now, I did, and I have worked in organic electronics for more than, I will say at this point, it's almost 20 years. And for the biggest part of that time, the overall goal was to really replicate what silicon electronics do, right? So we were trying to demonstrate that we could print diodes, photodiodes, detectors, obviously light-emitting devices, and that they will have a performance that is comparable to these, off-the-shelf components that you can buy. However, since I started working in solar cells, organic solar cells, the focus started shifting towards sustainability and actually why printing electronics gives you a better possibility to develop sustainable electronics. And so now a big focus in my group is how do you make electronics sustainable, and not only from the perspective of using materials that are coming from natural sources, but also from the perspective of how you make electronics, how do you design electronics that can consume less and less energy, right? And the idea with that is that hopefully we can get electronics that can be self-power. Okay.
So basically trying to reduce the product life cycle of those electronics.
Yes,
from the manufacturing to at the end of the life cycle.
Right, and we started learning about that again when we were starting conducting research in organic solar cells, which at the time, this was back in 2010 when I entered kind of that field, and obviously that the whole motivation of doing research in photovoltaics in general, right, is that we want to move to renewable energy sources. And so you start learning about this life cycle and of the technology, and that really gets you thinking, right, on kind of the bigger picture of, obviously there is ways to generate energy that generate a lot of greenhouse gases. We don't want to burn fossil fuels to do that. We can do photovoltaics, right? But very quickly your attention moves not only to that, right? But you need to ask, okay, why do we need so much energy, right? and a lot of the energy that we start, energy demands, the increases in energy demands, there's a big component that comes from all our consumer electronics, right? And the fact that all of these computers, phones, everything now demands electricity. And so
Yeah, that is a very interesting way of looking at it. I feel like a lot of the current products in electronics, they're always pushing for as much power as possible. Like the newest like phones, they're trying to add as much transistors into it.
yeah,
And
it's a way of thinking, right? And I recently read a quote, I don't remember by whom, that said that digital computing is the product of cheap energy, right? So what does that mean? It means that when you are not really conscious of the price that you pay to get energy into anything that you engineer or design, then you can afford to just add and focus on performance, right? And that's really what has happened since all the evolution of digital computing and digital electronics is the fact that we have always been pursuing performance, right? And that has been the metric, right? And we have built industries towards selling performance, right? And to me, that makes a lot of sense, actually, right? You want to build a big industry, you want to show that you can do more and more and more and more with the stuff, that the technology that you are building, right? At the end of the day, technology, that's the drive of building technologies, to make our lives easier, more comfortable, right? To make these processes faster for us. However, what is very interesting is that right around the time when I actually went into organic electronics and specifically organic photovoltaics, that's about the time where electronics actually stopped improving. So I was teaching my class yesterday, and actually I was telling people that the computers that I used a decade ago are not slower than the computers that I use right now, right? Actually, there are many places where the computers now are slower, or at least clunkier to use, right? It seems that things are not improving, and there's a few reasons for that. And some of the reasons is that, first of all, we don't use all the computing power that we have at our hands, right? Regular users, it's like our brains, right? Regular human being uses a very small percentage of our brain, and now we're in a position where we are buying electronics and we don't know how to use at its full capacity, right? And the question is not whether we know, for me at least, it's not whether we know how to use it, but whether the regular user needs to use all this capacity, right? And so, that gets into a different type of conversation as to, what are the economic drives of electronics, and they remain the same that they have been for the last, half a century, right? This increasing performance and increasing.
So do you think that can change in the future, or like?
It is difficult, unless we demonstrate that there is alternatives, right? And how do you at the end of the day, again, to me, I look at this as from a consumer perspective, right? And when you see consumers that are not happy, right, with the products that you are buying, and they are not happy because I need to recharge batteries all the time, I need to plug everything, right? I need to learn how to use it. There's so many compatibility issues, right? That have for those of us that lived through the first race of when Microsoft and Apple were really coming to the market, and there were all these compatibility issues of whether you use Mac, you use Apple, and then I don't know, something about 15 years ago that started to wash away, and then you had increased compatibility. But then we are getting back into these niches where everybody's defending their own turf, and now there's so many issues with the compatibility, and this website doesn't run on Explorer, and you don't have this website on Microsoft. So really, from a user perspective, I'm not happy, at least, with the technology as it stands now, right? And I think I'm not alone in that. Now, there is a lot of empty or promises that haven't been fulfilled, right? When 10 years ago, everybody was talking about wearables as, they're going to revolutionize. And in many ways they have. But they have not reached the level of adoption that we thought they were going to reach, right? Or they could, because I think, if you have wearable monitors, everybody will be interested in monitoring their health. But something that has happened is that a lot of the barriers for widespread adoption or people that adopted these early technologies, they just get tired of, again, batteries, clunky devices. So there is still a lot that can be done to improve many aspects of this technology that doesn't have to do necessarily with performance or with packing more functionalities into it, but that really had to do with kind of having a human-centric vision of it. And that's really the challenge, right? That things are not going to change as, everything in life, that there's inertias and technology giants have certain inertias of certain business models, and it's very hard to change it. And when your business model has been to put a new phone every year, to put a new computer or a new processor every year, that's what you do, right?
Sort of change the status quo, right?
Right, and so it's difficult to innovate, and certainly, if you look at the cycles of innovation, disruptive technologies happen not because you start competing with the big giants, but because you find niches where you show that there is, a real value for a user, that for user adoption, right? And where people will be willing to invest in an unknown technology and an unknown way to do things. And if you can show that there's a viable path, right, for that technology to have sufficient consumer penetration, then you get the chance to disrupt the industries, right? But that requires awareness, right? That requires people, engineers like you and people in my group, that they need to be educated in a with a different perspective, right? If we try to educate people to follow what the industry is doing, then things won't change, right? And that's part of what happened to me to some extent in recent years, was this awareness that, okay, I have been doing organic electronics with these goals of trying to replicate what silicon does, right? And silicon does it really well, and it always was kind of a moving target, right? And so, if you try to chase that, right, silicon's a very well, it's an industry, it's a well-established industry, and it's very hard to catch up, right? But then in recent years, through collaborations with people in interactive computing that had this idea of, we want to deploy computing objects, right, that can allow us to interact as humans with the digital world, but where those interactive surfaces, we don't want them to have batteries, we want them to preserve privacy, we want them to be deployed in simple objects in the world, and then you start changing the way you see technology and how you can develop technology, right? And so when you adopt that and you adopt power autonomy, for instance, as the guiding principle of the electronics as you conceive it, then you start realizing that following digital paradigms, following silicon, right, is not the way. It's not a viable way to get to where you want to be, right? And so obviously many people have realized this, and that's why part of the reason why you see all this emergence of neuromorphic engineering and computing, right? Because people realize that there is many things that you want to enable, like machine vision and all these learning algorithms that digital computing paradigms require a lot of power to drive all of this, right? But if you look at nature for inspiration, if you look at how neural systems work, then you realize that perhaps there is alternative ways to look at not only how you design the system from an computer and engineering perspective, electrical engineering perspective, right? but even from the materials that you use, right? Because the performance doesn't necessarily need to be, similar to silicon, right? Mm-hmm. Our neurons, when you look at the firing rates of our neurons, for instance, they're very slow, right? We tend to think in digital computing terms with clock speeds in the gigahertz rate, right? Neurons fire at kilohertz or even hundreds of hertz rate. So that completely removes some of the goals that you have when you are developing semiconductor materials, right? Because kilohertz can be achieved with materials that have 100,000 times the mobility that silicon has. Mm-hmm. And now you can have the luxury to say, well, I can have a material that will be slower, and that perhaps can give us also the luxury of being biodegradable or being produced with a much less energy than what it takes to produce electronics like silicon, right? Mm-hmm. Obviously, there is trade-offs, right? And this is what it's important for people to realize, is that, we have the digital computer paradigms, right, were developed around the idea that you will have a machine that could do everything, right? And so, that's why we use computers for everything, right? You can program these machines, you can use software to change the type of operations that they do, and you can do everything, right? From videos to text to calculations and all sorts of different things that obviously are very useful for humanity. But when you try to deploy intelligence, and by intelligence what we mean really is to have objects that will sense the world, right? Will sense interactions between humans and translate those interactions into the digital realm so that machines can operate on this. Those interactions, you don't need all-purpose computing paradigms to enable those interactions, right? So something that, for instance, it's a source of inspiration, is a little bit what nature does, right? Nature, and if you think in natural organisms, right? You have a central system of processing, right? That it's the brain. And then you have a bunch of sensors, right? That act and are peripheral to the brain. And these sensors do not require, right, to have a brain in them, right? All that they need is to funnel kind of the signals, to route the signals where they need to be. Mm. Furthermore, some of those processing that happens when especially in organisms like octopus, for instance, right? That is a completely different neural system than vertebrates, right? Octopus are very, very interesting animals because they have a decentralized brain, right? Its actual central brain is very small, but they have a lot of processing that happens at the local level, right? Mm. And so what that gives them the ability is just to sense the environment and almost immediately react to it in a very, very complex ways, right? They can change color, they can change shape, and none of that is mediated exclusively by the central neural system, but actually, there's a lot of processing that happens at the in this case at the arms, at the tentacles of these cephalopods. And so, what I think that points out to the fact is that, when we design wearables, when we design IoT sensors, when we design interactive elements in the world, these are objects in the world, right? Mm-hmm. We don't need to worry too much that we are not embedding these systems with all-purpose computing power, right?
And octopus are regarded as one of the more intelligent species.
Yeah, I mean, what is remarkable from a control perspective on an octopus is that they can change color and shape at the speeds that defy any central processing system algorithm.
And that's how they evolved, so then they can help fend off predators with these processes too, which is absolutely fascinating.
Absolutely, right? And the animal kingdom is really full of these things, right? When you look at the brain power that a little cockatoo, right? It has a very, very small brain. I don't remember the exact number. It's probably in the hundreds of milligrams of power of mass, right? And then perhaps a few thousand million neurons on it. Anyway, but compared to the size of the human brain, it's very small, and yet these birds can fly at super high speed through objects to complex fields of obstacles, and they can recognize prey, and they can do a lot of things, right, with very, very little brain power, if you will. And this is just because they follow a very different computing paradigm than what we use in digital electronics.
It's interesting how interlinked nature is with technology.
And it has always been, even in the development of the digital computing paradigms back in the 50s by Johnny von Neumann and some brilliant guys at Princeton, right? They were inspired basically by the central system of the human brain, right? They say, well, you should have a processing unit, and then you have some controls, and obviously the brain can do many things as well. It's a kind of an all-purpose computer, if you will, right? And so it has always been intertwined, but now we just need to look at from a different perspective, right? Is how is it that the brain not only processes information, but it processes it in a very, very efficient way, right? And that's where you get all the neural networks, and you get into that realm where you realize that you need to collocate memory and processing and sensing in the same units, and really, allow some parallelism, or build systems that can have a very high degree of parallelism in processing information, but also systems that are not necessarily entirely they are sort of probabilistics in many ways, right? And that's something that generally we don't tend to think when we develop computing systems and things like that.
Yeah, I think it's interesting that we kind of stick with like existing system, the von Neumann architecture, and then we kind of implement it in every aspects of like computing, like even to the smallest sensors. We're trying to give it a microchip, but I see that that is doing way more computing than what it should do. Why do you think that's the reason? Like, what's the reason behind it?
Well, I mean, I think we are all humans are animals of customs, right? And if you get trained into certain way of looking at the world, right? And especially if you don't get trained to innovate and to think different and outside of the box, then really it's not a wonder, right? That we keep repeating the same paradigms, right? And innovation is really always response to the necessity of doing something different, right? And so again, that comes I think on your personal motivation sometimes that say, well, I'm not quite happy with getting or building technologies that I know are affecting the planet, right? Because both destruction of materials are very damaging to the planet, or because of the waste that it generates, or because the energy burden that it increases, right? But you need to have that awareness, right? You need to have that. That needs to be something within, I think, the framework of your values that you need to identify as a relevant problem that you want to tackle, right? And then I think it also needs a little bit of, I don't know how to put it, but I think, you need to be willing to go against the grain, and you need to be willing to be told that that's not either possible or that it's foolish, or that doesn't have any value, right?
And there's like economical cost to implement these, and then there's like the other effects too if you fail.
From all the perspectives, right?
Yeah.
Sometimes when I tell people, for instance, okay, we are developing sensors that can only do that, right? And they look at me like, why would you do that? That's silly, right? You can do that with a camera, and that's it, right? And not only that, I can do 100 things more with that camera, right? And so again, how do you change the framework in which people see problems, right? It really depends on a lot of, your personal journey, I guess, through engineering, science, and even through life, right? Where I come from Mexico City, for instance, and Mexico City was a very polluted city when I grew up, right? So kind of environmental causes and issues have always been important to me in that sense of saying, yeah, we kind of have a responsibility as scientists and engineers of producing technology that, or the technology that we produce is going to have an impact in the world, right? And it's not that impact is not going to be constrained to the uses of that technology, but it's much broader than that, right? It's broader in the consequences that it has for human society, for environment, and so on. So, I think awareness is a big thing, and certainly I have seen that change dramatically in the last 20 years.
The social media technology, now there's so much more awareness about sustainability, and you said that your research shifted from when you first started.
Yep.
And there's more emphasis on sustainability now. So do you think that is because of the awareness from public, just society as a whole?
Yeah, no, and certainly, societal awareness has dramatically increased with respect to environmental issues, right? I remember when I came to the U.S., you will go to a supermarket and everything was plastic. And at the time in Mexico, we had already conversation about, let's try to phase out plastic out of the supermarkets and things like that. And in the U.S., it was a non-issue, right? Nobody was talking about this, and I was like, "Wow, this is insane, right?" But the U.S. has always been a society that at least for the last 50, 70 last years have, developed an amount of wealth and a sense of resources are infinite, right? And you can always grow, and you can always and it's not a problem. Right, to look at the consequences of this, increased consumption and not using materials that might end up in landfills that most of the time you don't even see, right? Because a lot of waste streams flow out of the U.S. and they go into other countries, right?
Like the regulation changes from country to country as well. So,
yeah, obviously, yeah. Right?
Yeah.
And coming from a country where you see some of that, you have an increased awareness, I think, of I want to work in a field where, I think I know that I'm having a positive impact into these issues, right? Obviously, that was not the initial motivation for me to study. Actually, I came to the U.S. to do holography, work with organic materials, but to do holography, right? And have always been a Star Wars fan. And when I realized that were people looking at how to make real-time holograms, I was like, yeah, I want to do that, right? So it's something that has slowly evolved, right? And obviously with, increased awareness in global warming and all of that, it starts to acquire a sense of urgency that otherwise probably wouldn't have had. Perhaps 30 years ago, I would have chosen a different path, even if I had some predisposition to be environmentally conscious. However, nowadays, I see it as an absolutely priority, right, to work in an area where I'm trying to contribute to develop technology that is more sustainable, that it's more conducive to preserve people's privacy, and there's a bunch of things that I don't like about our current technological world, and we are trying to find alternative ways in which we can contribute to give people a choice, an alternative, right? Because it's you cannot just point out to what is wrong with current technology, but you need to say, well, we can do things differently, right? You don't need a camera to do everything, right? You can use other type of sensing surfaces and technologies that might be more conducive to preserve your privacy, to that will not be required to be plugged into an outlet or use a battery that I know will have a strong environmental impact. So, but certainly, this type of or the opportunity to do work in this area, right, from a funding agency perspective and all of that, that has evolved and shifted dramatically, right? There's an increased awareness, and I think we're moving slowly as it is, right? But we are starting to have, especially, students of your generation. I see that, as being front and center of some of these concerns, right? People and students that come to me and say, I want to do something with sustainability and energy, and I'm worried about these things, and I want to contribute to do that. So I think certainly that I see things shifting, right? Now at an industrial perspective, that shift is slower, right? What we need is innovators, people that can take these novel ways to do things and show that you can actually commercialize and impact people's lives in meaningful ways, right?
Are there commercialized organic electronics?
I have not really, and that has with the latest things that I developed before joining Northeastern. I had, and I still have, I think, some the dream of commercializing some of the technologies that are coming out of our lab, but commercialization is difficult.
You think it's more manufacturing, or?
No, what is difficult it's really to find that niche that will show and that will resonate with people, and that will solve a real problem, right, for somebody, that will convince that somebody to spend money on what you're doing, right? And I had the pleasure and the fortune to participate in a couple of NSF programs that are called iCorp. So these are it's a 6-month program that the goal was to teach both professors, students, and people from academia to do commercialization. And I really loved it. I think it was fantastic because it really gave me the tools to identify that one of the first thing is that the problems that you think you are solving in the lab are not real problems most of the time.
Identifying the problem is what's like the important part.
It's the most important part, right? It's which is the problem that I'm going to solve, right? And so to get those answers, you are not going to find those answers with your colleagues. You're going to find those answers in an academic literature. You really need to interact with the real world, ask people, and try to identify where you can actually have an impact, right? And so it's a hard process to do, but I think it's very motivating. And unfortunately, once you are a professor, you have less time to do these type of things. But I have tried to encourage my students to go through that process and to go and explore and try to identify these niche problems where we can actually make something that will have value, right? Because I think once you start doing that, then you really have a real possibility to innovate and to start showing that what you do, it's different ways to do things, and it has real value for people.
Yeah, I find there's this center of like the academia and compared to the commercialization part of like doing research in that area, the R&D, the focus are very different. Like most of the academia, they're not really doing things that are more relevant to, for example, everyday people or like for businesses. And the commercial side, they're just trying to target questions. Like I find there should be some sort of a middle ground where there's that exploration, but also like just trying to solve problem instead of like having two distinct groups, sort of.
Yeah, I mean, there are several schools of thoughts about that, right? So when I was in Mexico, for instance, when I was studying physics, most of my teachers will tell me that doing applied science was corrupting, right? The field. Academia, right? That you should launch into these intellectual explorations for the sake of contributing to human knowledge, and that was it. That was sufficient motivation, right? And basic science is like that, right? And there's nothing wrong with this, right? But at the same time, you acquire knowledge for some reason, right? And if I learn something and I learn something that can have an impact into somebody's life, right? I think it's part of our responsibility as a community to also give this knowledge that input, right? At the end of the day, all the research that we do, it's funded by the public. To a great degree, it's funded by taxpayers' dollars, and I think it's our responsibility that those taxpayers' dollars have a return investment, right? And the return investment is that there should be people that is trained to take this fundamental knowledge and try to have an impact into the world. Now, it is difficult when you are in the academic world to really have contact with regular, normal people, right? And it has, at least to me, in many ways, it had a lot to do with perhaps a cultural barrier that, when I was in Mexico, there's a very hierarchical structure, right, where you don't talk to people of seniority in certain ways, where you don't feel entitled to go and ask the owner of a company, right, some questions, or where even your teachers establish a barrier by saying, oh no, you address me like sir, and you give me respect, and I'm all for respect and all of that, but that also established a barrier for the flow of ideas, right? So in many ways, when you get trained into this type of cultures, right, you have a barrier for innovation because you are not learning what the problems are, right? So you don't get motivated as to, okay, I talked to the CEO of this company and this is what they are trying to solve, and I think I have a solution and I think I want to work on it, right? And this was the big eye-opener for me when I did this NSF programs, the ICOR program, because the goal was to interview 100 people in a span of 6 months. And so that amounted to really, having to reach out to many, many people and really develop that skill of losing your fear of, so you need to pick up the phone and go to, can I talk to the CTO or the CEO of the company, because I want to ask questions, right? And so what you learn is that for innovation to happen, you need that. You need people that are trained and that have a hunger for doing this type of explorations, because that's the only way that you're going to find real problems, right? Now, what you were saying is correct, right? Industry, their goal is to make money, and they are trying to solve problems that will increase their market share and things like that. And so these are real world problems, right? They are seeing consumer demand and consumer what consumers are asking for, and they are trying to solve some of these problems, right? Where innovation, it's a problem sometimes is that, there's only so much room for them to change certain processes, to change certain structures, right? And if your business model, right, drives you to do certain things, it's very hard for you to say, well, I have a very good solution that requires you to dump all your factories and now you're going to use these things or this new material that does not require all these billions of dollars that you have invested in equipment to do and to work with this type of material, right? So there is a big inertia, and it's perfectly understandable that there is, right? But there is also the need for people from academia, right, that identify solutions to have and to take the risk to go and start something with the hopes that you're going to start changing, right, some of these dynamics, and that at the end of the day, you might grow into a small startup that, could be acquired perhaps by a big company or could grow into a big company, right? But that's the only way that you can really make that transition. And one of the biggest issues, again, is that requires a very special type of character, right? And the quest that, it requires one, students to be trained in entrepreneurship so that they know what tools they need, what kind of questions they need to ask, that when is the right time to incorporate, when is the right time, how do you protect what you're doing, and it requires resources at the end of the day as well, right? Institutions, professors, they need to be willing to, push students into that direction so that, entrepreneurship is not for everybody, just as professorships are not for everybody, right? You need to have certain character and certain motivations, but you need to find those students that will, take the step and the risk and say, yeah, I'm willing to, start something fresh and with a high risk, with the possibility that I'm going to have a very high reward, as opposed to just go to a company and join the efforts to solve certain problems, right? So that's part of what I have seen changing as well in the last 10 years, right? Even from academia, there is an increased awareness that we need to do that. Now, professors, we are not generally trained to do that, right? And that's one of the biggest issues, right? And that's why you have NSF efforts and some other efforts from institutions to try to train the student in entrepreneurship and even faculty, right? In everything from protecting the generating the IP that you need to protect, what the technology that you are generating, to how do you go and, who do you ask for funding, what kind of funding sources exist, and so on. So it is complex. It is a complex journey, right?
And an example of like the innovation changes, like reusable rockets, right? And like how we transferred from like having to like throw so much out in space or like in the oceans, and now we can return and we save so much more. But since we broke that ice, now it's like it's smooth sailing, but it was hard to break that ice, and it's hard to innovate from how it was for so many decades.
Yeah, and it requires for people to take risk, and risk are real, right? It's not the risk of just losing money. It's just your career risk. You have goals in life, and some of these, put the strains on families. And if you want to start a family, you probably, think it twice if you say, well, I might lose completely my income, and my income might not be secure because I'm working in something that I don't know if it's going to turn out to be successful, right?
It takes time too.
It takes time. It takes time, and for the longest part, I think, when I went through these, for instance, these NSF I-Corp programs, there was very little tolerance for risk in hardware, investing in hardware. Very, very difficult, right? So actually, I went trying to commercialize not an organic electronics product, but actually a photonic product that at the time we thought it was kind of an ultra-fast shutter that we thought it could be used for lasers in manufacturing, just to shape the pulses of lasers that are used in manufacturing. And when we were talking to VCs and people, they were saying, well, how much money do you need, right, to start this up? And I was like, well, I need to fabricate the mirror, the element that will allow you to do this shutter. I need a deposition system that is $500,000. I need perhaps a clean room that's, a small clean room. That it very quickly adopts to the millions, right, when you are trying to do hardware. And, people look at you like, why will I invest in that when I can just put $50,000 to a software company and my return on investment is in 2 years, and I can have the possibility of having something, a very big return on investment, right? And so that was kind of the general kind of atmosphere that we felt, and that's why we pivoted many times. We identify a few things, and then at the end of the day, we decide not to continue that. For me, it was more than I'm not going to form a startup. It was just, I'm not going to keep working in optics because this is crazy. I'm never going to be able to start something if I need a $500,000 laser and if infrastructure-wise, it gets very expensive to work in hardware.
The difference in like innovation between software and hardware
is dramatic, right?
Yeah.
It's completely dramatic. Now, that is changing, right? COVID started changing this, right? Because all of a sudden you realize that if you don't produce hardware, you are depending on regions of the world that you don't control, on global events that you don't control, and all of a sudden that exposes you as a country. And we have been saying that for a long time, and it was, everybody look at us like, well, yeah, that's fine, but globalization is great. It's all our factories and China or Taiwan, and it's fine. Everything, that system, it's going to work fine, right? But then you have an event like COVID, and all of a sudden you cannot have chips, and if you don't have chips, and your dryer, your phones, your little clock needs an IC, and that IC cannot be brought from China because there is a pandemic, then that starts to become a big, big issue, right? So I think that is changing people's awareness that we need to produce hardware, we need to invest in hardware, and that is very important. And that's one of the things that I like about organic electronics is this fact of saying, well, in principle, the level of investment that you need to produce organic electronics is orders of magnitude smaller than what you need to produce silicon electronics, right? And so, we might not be able to produce a CPU with an organic electronic technology, but certainly there's many things that we can replace and that we can enable local fabrication of electronic components, sensors, and products that can bring value, and that at the same time you are not only addressing sustainability but also resilience. And to me, resilience is the other axis that is very important, right? Not only you need to have electronics and technology that is sustainable for the health of the planet, but if for the health of humankind, we need to have technology that is resilient, right? And so something that I have always kind of worry about is we depend so much on the cloud, and the cloud obviously gives us the ability to do wonderful things. But what happens if that cloud system fails for whatever reason, right? If a storm goes and knocks out the power of one of these data centers, and now we cannot access data, our whole system collapses, right?
Yeah, and like all the system that built to prevent those things happens require them to build more.
Exactly.
And yeah, that's just like you're adding more complexity upon the complexity. So.
Yeah, and again, I just want to be very clear that I think that complexity will be needed. It's just there is so much overhead that are and a strain that is put in these systems at the moment, because we want our fridges to be connected to the we want our
Cars.
the cars, if it's an autonomous device, probably it's necessary, but we want everything to be connected to the cloud and to be accessible through an app, and that's probably fine, but we need to find innovative ways to do that, right? Because these edge intelligence, edge technologies, right, they don't always need to be linked to a central system, right? And if you just manage to create technologies that are more self-sustainable, right, not only in terms of power, but in terms of the intelligence and the processing capabilities, right, so that they don't depend on, the data center that is located who knows where, and if that data center loses power, then we cannot do anything, right? I think it's a necessity that we start thinking in ways that we build these technological systems so that they are more resilient, right? Because I think we have all been there when you lose light in your house, you lose power, and then you feel like you are back in I don't know a century ago, right? You cannot do anything. You cannot. Yeah, you can. Actually, it was funny.
Internet too.
Actually, it was a funny story because we recently lost power in my home, and my kids. So when I came to the U.S., in my case, I only had music, CDs, and books, and since then I have. Kind of stopped buying much CDs, but I have bought a lot of movies because I really like movies. So those are my three things: books, CDs, and movies. And my kids have always looked at me as like, why do you bother buying these things, right? And so the other day we lose power and we have a little, battery generator, and I was like, well, do you want to watch a movie? And it's like, how come, Daddy? There is no internet. There is no. It's like, oh no, but you have the physical object that you can actually play, and you have a little power that powers your laptop. You actually can do things. You still can operate at certain level, and I think we need to really go back to this idea that we need to build resilience into the systems that we are building. And I think part of the reason why I like so much photovoltaic energy generation is at least that gives you that energy independence, right? Or the possibility of that energy independence in an event that the grid goes down, or that there is a natural event that will, cut down the power of the grid. You have that at your home, right? And so that gives you a sense of security. I can run the AC, perhaps I can run the heat in my power. I can perhaps access internet or do something else, right?
Do your kids enjoy the movies that you put on during the blackouts?
No. most of the movies that I have are not kid friendly yet. They are getting there. We do have a few cartoons, and they did enjoy that. But yeah, I mean, I think it was very clear to them at that moment. It's like, oh yeah, actually there's some value in having physical objects that you can interact with, right? Books. My daughter, she's an avid reader, and she has a Kindle, and I'm amazed by how many books she has read, and certainly that has opened the door for her to read way more books than the ones that we could have even buy or accommodate in our house, right? So there is real value to these digital technologies, and there's not, we shouldn't see this as a crusade against digital technology, but it's just how do we build those extra layers that we need so that we, ease some of the pressures that put both on the environment, power, and some of the physical resources of the planet, but in a way that, we can still enjoy some of these facilities, right? Because you have a Kindle, you read a lot, but then if the light is out and she cannot upload or download things, well, you still have books that you can open and read, and So I think it has value, right?
And I don't think we lose the physical component of it, like the reading versus on paper versus digital. It's a completely different experience for me as well.
Yeah, well,
right.
That's a different conversation, really,
yeah.
right?
Yeah.
I have been forcing myself to read on digital platforms, right, on the screens, and I thought I never would be able to do it, and now that's mostly what I do. I still like the physical copies and the feel of paper, but for many practical purposes, right, it's just not that convenient to be printing out papers, for instance, right? And it's wasteful. You read them once and then you toss them, or you need to carry all this paper, right, from place to place to read, for instance, articles for research, right? And so there's real convenience to these things, but there's also certain places for physical objects that they still need to have. We are still in this real world, and we need to interact with physical objects, right? And so I think the vision that, I don't know if you have heard about Mark Weiser, which was one of the fathers of ubiquitous computing, right? Was the guy that coined that, and his idea was really to deploy intelligence in the objects of the world, right? To make smart objects in a way that we could interact with objects, not with a virtual reality, right? And so I think that's a vision that I like better than this version of technology where we are just always drawn to screens. We are always drawn to these virtual worlds that I think takes something off our human experience, right?
Okay, so we will have this last question for our podcast. So most of our listeners are probably for our generation. So what is one advice you want to give for the next generation of people?
Well, I think you need to challenge yourself, right? I think, we live in a world with many, many problems and challenges, and nobody's going to fix them but you. Unfortunately, and I think, people from my generation and you, as you grow old, you acquire responsibilities, you acquire, it's more difficult to you to take risks. And so, you need to take risks, and you need to try to make an effort to impact the world in a way that we, the older people, sometimes cannot, even if we we see the problems, even if we have the best intentions to affect them. Sometimes, we are just bound to certain constraints that we have built in our life, and it becomes more difficult, right? Like founding a company that will exploit things, right? I would have loved to do that when I was younger, but I have always had this. My passion has always been knowledge and science and technology. So even though I identify that, I wish I had another life where I could dedicate my life to innovate, right? Rather than following these more intellectual, perhaps, pursuits. But, the younger generation, you have the time. And that happens, I remember when I was your age, and you do have the time. And you need to take risks, right? You need to really try to push for things to change. And I think you have at your disposal many resources. You're a very privileged generation in terms of the resources that you have. And at the same time, you are at a very high risk of losing yourself in this, sea of hate and social media and infinite scrolling through things that are completely, that are not going to bring good to anybody necessarily, right? And so, to some extent, I feel very excited about the possibilities and to see how your generation is reacting to some of these big problems, because I do see a real commitment. I do see that energy, right? And at the same time, I do see also that risk of losing yourself in things that or quests that seem too big or too uninteresting, right? This need for instant gratification, it's very dangerous. It's very dangerous, because almost no enterprise in life that is worth it, you get instant gratification, and unfortunately, technology, it's built to give us that rush of instant gratification, and so I see that even in my kids, right? They want everything fast. Everything needs to be fun. Everything needs to, and there are certain things that require discipline, and that's it. You need to go through and carry and just persevere, and eventually you get to the place where you can have an impact, right? A real impact.
Right. Very well said.
Thank you for the conversation.
No, thank you. Thank you for the invitation.
Yeah.